Welcome to this lecture on one of the most fascinating paradoxes in nanoscale materials science, the fracture strength paradox. Nanowires and nanotubes are incredibly strong, often approaching theoretical strength limits. Yet, they can catastrophically fail under the tiniest perturbations, like a single atom adhering to their surface. At the nanoscale, materials like carbon nanotubes and silicon nanowires are nearly defect-free. They lack the dislocations, grain boundaries, and voids that plague bulk materials. But here is the paradox. Despite this near perfection, they can snap catastrophically when something as small as a single molecule lands on their surface. Imagine a flawless carbon nanotube on the left, pristine and strong. A single atom or molecule adheres to it, and suddenly the entire structure fractures. Why should we care about this paradox? Because it fundamentally limits the application of nanomaterials in real-world engineering. Carbon nanotubes can have tensile strengths exceeding 100 gigapascals, roughly 100 times stronger than steel. Yet, this extreme sensitivity to surface effects makes them unpredictable and unreliable in ambient conditions. Let us start by understanding what we mean by theoretical strength. The theoretical strength of a material is the stress required to break atomic bonds in a perfect crystal. A rough estimate is that theoretical strength equals Young's modulus divided by 10. For carbon nanotubes, Young's modulus is approximately 1 terapascal or 1 trillion pascals. This gives a theoretical strength of about 100 gigapascals. Remarkably, experiments on individual pristine nanotubes have measured strengths between 50 and 100 gigapascals, very close to this theoretical limit. In bulk materials, defects are everywhere. These defects dramatically reduce strength below the theoretical limit. Griffith fracture theory tells us that strength depends inversely on the square root of the largest crack, or defect size. The fracture stress equals the square root of 2 times Young's modulus times surface energy divided by pi times crack length A. For bulk steel with micron-scale defects, this predicts strengths of only a few gigapascals, far below theoretical. Picture a bulk material riddled with defects, voids, cracks, dislocations. Each one is a potential failure point that concentrates stress. Now consider a nanomaterial. At dimensions below 100 nanometers, there is simply no room for large defects. The probability of a defect scales with volume. A nanotube with a diameter of 2 nanometers contains perhaps 10,000 atoms. A bulk wire contains trillions. Chemical vapor deposition and other growth techniques produce nanotubes and nanowires with extraordinarily few defects. This is a schematic of a perfect nanowire lattice. Every atom is in its ideal position, creating a flawless crystal structure. If nanomaterials are so perfect, why do they fracture under tiny perturbations? This is the heart of the paradox. At the nanoscale, the surface-to-volume ratio becomes enormous. For a 2 nanometer diameter nanotube, nearly half the atoms are surface atoms. The surface-to-volume ratio scales inversely with radius. As radius decreases, surface effects dominate. Surface atoms have dangling bonds and are chemically active. They readily bind to adsorbates from the environment: oxygen, water, organic molecules. When a molecule adsorbs onto a nanotube surface, it does not just sit there passively. It creates a local stress concentration. The adsorbate forms chemical bonds with surface atoms, pulling them slightly out of position. This creates a local strain field. Here is a nanotube with an adsorbate on top. Notice how the local lattice distorts. Stress concentrates in this region, shown by the arrows radiating outward. For a small perturbation, the stress concentration factor can reach 3 to 10 times the applied stress. Local stress equals the stress concentration factor, K sub T, times the applied stress. If K sub T is 10, then an applied stress of only 10 gigapascals can create local stresses of 100 gigapascals, reaching the theoretical strength. Let me give you an analogy. Imagine a perfect glass fiber, incredibly strong in tension. A pristine glass fiber can support enormous tensile loads relative to its tiny cross-section. Now touch it with your finger. The oils and moisture from your skin adhere to the surface. The glass fiber with surface contamination. These tiny droplets create stress concentrations. Under load, the fiber snaps at one of these contaminated sites. When you pull on the fiber, it fractures at the contaminated region. The fingerprint, something microscopically small, causes catastrophic failure. This is exactly what happens to nanotubes. A single adsorbate acts like that fingerprint, creating a weak point where fracture initiates. Let us develop a more quantitative understanding. When an adsorbate binds, it changes the local surface energy. The change in surface energy equals clean surface energy minus adsorbate covered surface energy. For graphene or nanotube surfaces, the clean surface energy is about 1 to 2 joules per square meter. Let us use gamma clean, approximately 1.5 joules per square meter. When molecules adsorb, they passivate dangling bonds and typically reduce surface energy by 20 to 50%. So delta gamma is approximately 0.5 joules per square meter. This energy reduction creates a thermodynamic driving force for crack formation at the adsorbate site. We can apply Griffith's fracture criterion, but now considering nanoscale dimensions. Fracture stress equals square root of 2e gamma over pi c, where c is the critical crack size. At the nanoscale, the critical crack size is set by the size of the adsorbate perturbation, typically a few nanometers or even atomic dimensions. Let us say c is approximately 1 nanometer, the size of a small molecule. Let us plug in numbers for a carbon nanotube. Young's modulus is 1 terapascal, surface energy is 1.5 joules per square meter. Fracture stress equals square root of 2 times 10 to the 12 times 1.5 divided by pi times 10 to the negative 9. This gives approximately 30 gigapascals. This is significantly below the theoretical strength of 100 gigapascals. So a single adsorbate can reduce the effective strength by 70%. This is a dramatic effect from something so tiny. You might ask, why does this not happen in bulk materials? They also have surfaces that can adsorb molecules. In bulk materials, the volume dominates. Surface adsorbates affect only a thin outer layer, perhaps nanometers deep. The bulk carries the load. Moreover, bulk materials already contain much larger defects, micron-scale cracks and voids that dominate failure. Surface effects are negligible by comparison. In bulk, the surface layer is a tiny fraction of total volume. Adsorbates here barely affect overall strength. At the nanoscale, surface and volume are comparable. Half your atoms are surface atoms. Surface effects cannot be ignored. Experiments beautifully confirm this paradox. Let me describe some key observations. When carbon nanotubes are tested in ultra-high vacuum with atomically clean surfaces, they exhibit strengths approaching 100 gigapascals. When the same nanotubes are tested in ambient air, strength drops by a factor of 2 to 3 to 30 or 40 gigapascals. Researchers have systematically exposed nanotubes to controlled amounts of oxygen, water, and organic molecules. Strength drops correlate directly with adsorbate coverage. Here is a bar chart showing nanotube strength. Ultra-high vacuum gives 100 gigapascals. Ambient air drops it to 60. Humid conditions further reduce to 40. What does this paradox mean for practical nanotechnology applications? Maintaining pristine, defect-free surfaces in real-world environments is extraordinarily challenging. One approach is chemical passivation, deliberately coating nanotubes with a protective layer that prevents harmful adsorbates while maintaining strength. Embedding nanotubes in polymer or ceramic matrices can shield them from environmental exposure. But there is a trade-off. The protective coating or matrix must bond strongly to the nanotube, or else load transfer is inefficient. Ultimately, the fracture strength paradox represents a fundamental limit on the reliability of nanomaterials in ambient conditions. To truly understand this paradox, we need to think about the quantum mechanics of chemical bonds. Carbon-carbon covalent bonds have a specific breaking strength, determined by the overlap of electron orbitals and quantum mechanical energy barriers. The carbon-carbon bond energy is approximately 3.6 electron volts per bond. To break a bond, you must stretch it beyond its equilibrium length. The force peaks at about 10 to 20% strain, then drops as the bond ruptures. This is a schematic force-distance curve. Force increases with stretch, peaks, then drops to zero as the bond breaks. When an adsorbate binds, it pulls on nearby atoms, pre-stressing them. They're already partway up that force curve, before any external load is applied. Therefore, less additional external stress is needed to push them over the breaking point. The adsorbate has done part of the work already. Can we engineer materials to avoid this paradox? Are there strategies to maintain high strength despite surface sensitivity? One promising approach is core shell nanostructures. Use a strong core material like a carbon nanotube, then coat it with a chemically inert shell. The shell must be lattice matched to avoid introducing strain. Boron nitride nanotubes coating carbon nanotubes is one example. Here is a core shell nanowire. The inner core provides strength. The outer shell protects against adsorbates. Another approach is functionally graded interfaces, where composition gradually changes to avoid sharp stress concentrations. These are active research areas. We do not yet have a perfect solution. The progress is being made. Interestingly, biological materials face similar challenges and have evolved elegant solutions. Collagen fibers and tendons are nanoscale structures, just tens of nanometers in diameter. But biology uses hierarchical organization. Nanofibers bundle into microfibers, which bundle into fibers, which form tendons. Biological materials also use sacrificial bonds, weak crosslinks that break preferentially, dissipating energy and preventing catastrophic failure. Biological hierarchical structure. Strong nanofibers in green, connected by sacrificial bonds in red. When overloaded, red bonds break first, protecting the green fibers. We can learn from biology. Hierarchical design and sacrificial elements may help synthetic nanomaterials overcome the fracture strength paradox. Let me give you a more complete mathematical framework using linear elastic fracture mechanics. The mode 1 stress intensity factor K sub I equals applied stress times square root of pi A, where A is crack length. Fracture occurs when K sub I reaches a critical value K sub IC, the fracture toughness. Fracture toughness equals square root of 2E gamma, where gamma is fracture energy. Combining these gives fracture stress equals K sub IC divided by square root of pi A, which equals square root of 2E gamma over pi A. For nanotubes with adsorbates, A is the size of the molecular perturbation, around 1 nanometer. Plugging in A equals 1 nanometer gives the dramatically reduced strengths we calculated earlier, around 30 gigapascals instead of 100. There is another fascinating aspect. Fracture statistics become size-dependent at the nanoscale. Fracture strength in materials typically follows Weibull statistics, a probability distribution reflecting the weakest link principle. Failure probability P sub f equals 1 minus exponential of negative sigma over sigma 0 to the power m times volume 5. As volume 5 decreases, the probability of containing a critical defect decreases. Nanomaterials are more likely to be pristine. However, if a defect exists, it is catastrophic because there is no redundancy. One adsorbate can doom the entire nanowire. How do we actually measure these effects experimentally? Atomic force microscopy, or AFM, is the key tool. An AFM tip deflects a suspended nanotube while measuring the applied force with piconewton precision. Here is the setup. A nanotube is suspended between two supports. The AFM tip pushes down in the center, bending it until it fractures. The force versus deflection curve reveals elastic modulus and breaking strength. Changes in these curves before and after adsorbate exposure quantify the effect. Advanced AFM can even image individual adsorbate molecules, allowing direct correlation between adsorbate position and fracture initiation site. You might wonder, are there any nanomaterials immune to this paradox? Noble metals like gold and platinum are chemically inert, so they absorb fewer reactive species. Gold nanowires show less sensitivity. However, gold and platinum have much lower intrinsic strength than covalent materials like carbon or silicon. You trade chemical stability for mechanical strength. Diamond nanowires are an interesting case. Diamond has extremely high strength and is relatively chemically inert, but synthesizing perfect diamond nanowires remains challenging. Let us consider the thermodynamics of adsorbate binding. Why do molecules stick so readily to nanotube surfaces? The Gibbs free energy, change delta G, equals enthalpy change delta H minus temperature T times entropy change delta S. Adsorption is usually exothermic, meaning delta H is negative. Chemical bonds form between adsorbate and surface, releasing energy. Entropy change is relatively small. The adsorbate loses translational freedom, but this is partially offset by surface relaxation. The net result is delta G less than 0, meaning adsorption is thermodynamically favorable. Typical adsorption energies range from 0.5 to 2 electron volts per molecule, strong enough to be effectively irreversible at room temperature. How fast does a crack propagate once initiated at an adsorbate site? Crack velocity in brittle materials is typically about 10% of the speed of sound in the material. The speed of sound in carbon nanotubes is approximately 20 kilometers per second, incredibly fast. So crack velocity is around 2 kilometers per second. For a 1 micrometer long nanotube, fracture occurs in about 500 picoseconds. It is essentially instantaneous. There is no time for any crack arrest mechanisms or self-healing processes. Once initiated, fracture is catastrophic and complete. Let me conclude by highlighting some open questions and future research directions. One grand challenge is designing nanomaterials that can self-heal after adsorbate-induced damage, perhaps using mobile atoms or dynamic bonds. Temperature effects are not fully understood. At cryogenic temperatures, adsorbate mobility is frozen, but thermal vibrations that aid fracture are also reduced. Multi-walled nanotubes have redundancy. If the outer wall fractures, inner walls can still carry load. But inter-wall interactions complicate the picture. If a nanotube has both structural defects and adsorbates, do their effects add, multiply, or show more complex synergy? Let me summarize the core of the fracture strength paradox. Nanomaterials can approach theoretical strength because they have almost no bulk defects like dislocations or grain boundaries. However, their enormous surface-to-volume ratio makes them exquisitely sensitive to surface perturbations. A single adsorbed molecule can create a stress concentration sufficient to initiate catastrophic fracture, reducing strength by 50 to 70%. This paradox represents a fundamental limit for real-world applications of nanomaterials in ambient environments. Overcoming it requires creative engineering, surface passivation, core shell structures, hierarchical design, and learning from biological materials. Thank you for joining me in exploring this fascinating paradox, where perfection meets fragility at the nanoscale.